I really am quite honored by this and surprised, honestly. And really, it means an enormous amount of me coming from this community that I've worked with for so many years. And my computer, oh, you see, you'll believe me that I have to type in my password. But this community that I've worked with for so many years, I think is a wonderful community. Oh, okay. Okay, hold on for a second. Okay, there we go. So I'm doubly honored to have the opportunity to speak to you today about work that I've done, but really represents my participation in many collaborations and really some themes that we've developed at Purdue over the last few years, and with a variety of colleagues, one of which actually isn't listed here, which is Melba Crawford, who we've sort of developed this concept of this theme of integrated imaging. And it's a term, I think, I mean, I'm sure if you look on the web, you can find somebody else who's using it, but it's a term that we've sort of coined to represent, I think, what we think of as the next generation of imaging innovation. And, you know, this electronic imaging symposium was formed, I think, in the early days back, you know, when IS&T was the, I forget exactly what they were called, but the Photographic Society, I believe. And, you know, originally there was chemical imaging, and then people said, well, gee, there's going to be electronic imaging is going to eventually displace chemical imaging, and that happened with silver halide passing on, and now, you know, with electronic sensors. And of course, the next step there was to not just electronically capture, but also computationally process information that you had electronically captured. But sort of the next step beyond that, I kind of imagine, or we kind of imagine, is really not just the development of algorithms where people throw things over the wall, as they throw data over the wall from a sensor, but where you jointly design the sensor and the algorithm in the context of an application to solve a problem. So it's sort of another design envelope, you might say. And that's sort of the theme of what I'm going to try to talk about today. My concept here, or the concept, my belief, is that traditional sensor design is reaching its limits. For many years, people who designed sensors, you know, they wanted to get their job done, so the easiest thing to do was just to keep making the sensor better. So for instance, you have, let's say, an electron microscope, and you keep correcting errors. If it's broken, you adjust the screw to fix it. You make the correction. That made more sense. It was economically a better approach to getting more quality, more information, more resolution. But as the design limits were being reached, the cost of making those kinds of improvements is exponentially increasing. So, you know, a good transmission electron microscope might be $1 million. A very good one might be $5 million, and an extremely good might be $100 million. And that's a very steep cost curve. So people are starting to think about, well, it's difficult to measure only one thing very precisely without any contamination. And it's no longer possible always to fix the device in a cost-effective way so you get one pure pixel, right? So instead, the concept is, rather than making pure measurements, make the most informative measurements. So try to take the most information you can, and through tight integration of the sensor and the algorithms, convert that information into an image that's of the highest quality. Okay? So, it's sort of based, this concept is sort of based on what a colleague of mine, Mark Bell, calls Mick Jagger's theorem, okay? Which is, you can't always get what you want, but if you try sometimes, you can get what you need. And the problem becomes that, you know, we can't always get exactly what we want, but maybe we can get what we need. And really, the key then is, what is it that you want to measure that contains the most information that you can use to form the image that you want the most precisely? So typically, the idea is then, rather than try to measure one thing at a time, instead you measure a lot of things that are maybe not exactly, they're corrupted, they're mixed together, they're noisy, and then from that, you try to form an image, and that is done computationally, and it may be done adaptively, where there's a feedback between the sensing system and the actual image formation process. And And the idea here then is a key component of this is inverse problems, because the inverse problems are typically the machinery that you use to form the image once you've collected the data. And one disclaimer I want to make early on here is just that my talk is just going to scratch the surface. There's lots of work out there in things like coded aperture imaging and computational photography that falls into these themes. But I'm just going to talk about some of the things that I'm most interested in or doing, or not most interested in, but working on that hopefully tell a story that illustrate this. So I like to show this picture because to me it's an argument for the fact that inverse problems represent a really fundamental area of human study, research, that should be around for a long time. Because when you look at this picture, you're essentially instantaneously solving an inverse problem. And I think the plenary talk we had yesterday sort of described this and motivated it. But you look at this, you see, you recover the 3D depth information. You have a concept that this is a liquid. You somehow solved equations in your mind, presumably, and you determined that some event occurred that caused the splash. That's a very complex sequence of nested inverse problems that's very difficult. So inverse problems are an important component of what I'll be talking about. And there's lots of different ways of solving inverse problems, but the way that I've really become very interested in over the years, because of its generality, is what I'm going to characterize as model-based iterative reconstruction. This is sort of a name I've assigned to something that I think is practiced by a lot of people in different frameworks, but the basic idea is that you have a physical system from which you make a measurement, and then you have a mathematical model of the physical system, and you try to find an input to the mathematical model which fits the actual physical data. But a key component of that is a prior model which describes what it is that you expect your solution should have and, as its characteristics. And that's a key issue because it's sort of a dangerous road. Typically, people with physics backgrounds and physical sensing backgrounds feel uncomfortable with this prior model component. But it's essential because the alternative in many cases is that without a prior model, the problem simply can't be solved. Or essentially, there's a bias-variance trade-off. And if you're only accepting zero bias, the variance in your estimate can go towards infinity. So in practice, for the problems I'll be looking at today, I mean, there's more than one way of solving an inverse problem like this. But I usually take an approach where it's a Bayesian approach where there's a probability distribution for the observations given the unknown x, and then this prior model is a probability distribution x, and you have you solve an optimization problem where you try to balance these two terms. So there's the intuition for this. If I've sort of developed a viewpoint for intuition into this, and the idea of the prior model is that very often for real images, I mean, or really for any real image, the images live on what I like to call a thin manifold. So this kind of line describes where the images actually fall. And if you know every pixel in an image except for one, then everybody who works with images knows that you can, for any real image that occurs in, physically, that pixel can be replaced with high certainty, right? So if you know every other pixel, you can guess what that pixel is with high certainty. And if you think about that, that means that if you imagine this is like a two-dimensional image, a two-pixel image, if you know one of the pixels, x2, then the other pixel can be determined by finding that location and with high certainty. And that means that this manifold must be thin. So that's essentially a proof that the manifold must be thin, but there's still some uncertainty, so the manifold is not perfect. It doesn't have zero thickness, right? And that uncertainty is represented probabilistically with the prior model. And then the measurements, if you make a measurement along this direction, then then you know the solution must fall along this manifold if it's a linear forward model, so that the actual reconstruction has to fall at the intersection. So the key idea here is that this manifold provides a very strong constraint on the solution. And it means that the number of measurements you actually make only needs to be on the order of the dimensionality of the manifold rather than the dimensionality of the underlying space. And a lot of concepts in recent mathematical theory have really exploited this idea in various ways. And so the manifold plays a key issue in the process, and I'll try to argue that later. So the recipe for integrated imaging is to design a sensor to measure the most informative data, and then solve an inverse problem. And we'll see that there's often an enormous amount of synergy between the forward model of the sensor and the prior model of the image. And then this really creates sort of an explosion of possibilities, because you can start mixing together all kinds of different modalities, multimodal systems, all kinds of different data, put the models together and form images in all kinds of different ways. And I think we're beginning to see that in the field, this kind of explosion of all the intersections of the different modalities. So let me start off with some examples. So the first example is work I've done with Ken Sauer and Jean-Baptiste Tabal and Zheng Xie at GE, and Ken's at Notre Dame. And this is over many years. So CT is maybe one of the most classical examples of an inverse problem that has to be solved. So in a CT system, this is a GE CT scanner. You have an X-ray source, and the X-rays propagate through, say, a patient, and they're along approximately a line. And then there's a detector, which is thin and curved. So you might think of this as an imaging sensor that's thin and long. And typically, it will have, like, in this GE scanner, it will have 64 rows and about 1,000 columns. So in addition, the entire system is mounted on a gantry that rotates at around 3 rotations per second, and the patient translates through at constant velocity, so the path is helical. So this is what's called helical multi-slice. The multi-slice refers to the fact that there are multiple rows of the detector. When the scanner manufacturers started putting multiple rows in CT scanners, that revolutionized the business, because it allowed you to scan the patients much more rapidly and also perform different kinds of scanning procedures like cardiac imaging. So in any case, so this is the concept. And one key that's very important here is that because of the width of this detector, the beams travel obliquely through the planes that are reconstructed, so that it's actually a 3D reconstruction problem. The cone beam causes the interactions in 3 dimensions that you have to account for. So you can apply this kind of model-based iterative reconstruction, MBIR approach, and this becomes the scanner, and you have a 3-dimensional sinogram, so you have views, you have channels, and you have rows, so it's a 3-dimensional data structure. And you have a model for the forward projector, and you take the difference, and you apply the prior model, and you get a reconstruction. So then the key then becomes picking the forward model, picking the prior model, and doing the optimization. Okay? And one thing, so this just gives a little bit about information about the forward model. Obviously, I'm just kind of giving you the highlights here, but you take the photon counts at each detector. You have to take the negative log, because that's related to the line integral of the projections to the object. But what's really important and can be accounted for in this kind of model-based reconstruction approach is the uncertainty of those measurements. So it turns out that the projections are going to be noisy for 2 reasons, the photon counts and also the electronic noise. And you can calculate an approximate estimate of the variance of these photon counts. And that is very important, because it says that some of the projections are going to be more certain than the others. So when you're solving this inverse problem, you want to weight the projections which are more certain more heavily, and that's an important component of how you can improve the results. So in addition, then you have a prior model, and this is a very kind of simple prior model, but it can be very effective. We use what's called the Markov random field prior model, so that the probability distribution of the prior has what's called a Gibbs distribution. So it's an exponential of a sum of terms, where the terms correspond to differences between neighboring pixels in 3 dimensions. And the 3-dimensional regularization or prior modeling is very important. So in the end, then, the log prior just corresponds to a sum of functions of differences between pixels. And this function then penalizes large differences more. But a key issue is the selection of this function so that it preserves edges by not over-penalizing. And there's a particular function we choose. I mean, there's a lot of people that choose different kinds of functions for this. But for this application, we choose a function which kind of blends the behavior between an L2 case, where that would be corresponding to a Gaussian prior, and an L1 case, which is like a total variation prior. So this sort of blends between those by being L2-ish near 0, and as you move further away where edges are presumably being formed in the image, then it behaves more like an L1 norm. So I won't go into a lot of detail on this, but this can be fit to the data. And then, of course, you have to solve an optimization problem, and I could give an entire hour talk easily. You know, I could give I can teach an entire course on all the optimization techniques that are going on. And this is a very active area of research, but I'm not going to talk about it very much today because these are very computationally expensive problems, and being able to do them efficiently, computation efficiently, is an important, essentially, barrier to really wide adoption of these methods. Because mostly I'll be talking about a method called ICD today, which is a pixel-wise optimization, but there's a lot of research going on in having to do with non-homogeneous updates, preconditioning methods, what are called order subsets, nested optimization, multi-resolution targeting, and there's things called ADMM and augmented Lagrangian methods. This is a very active area of research. But I think the one thing I want to leave you with is that I have sort of a folk theorem, which is that these algorithms can be very computationally intensive. They might take hundreds of iterations to converge. But I have a folk theorem, which is that if you put a bunch of PhDs on it for a few years, eventually they can get convergence in these algorithms between 3 and 6 iterations. And it's really quite amazing. Here it shows that we can, in typical cases, get convergence of these algorithms in about, less than 6 iterations. And that's where each of these iterations is about twice the computation, theoretically, of the conventional reconstruction. But there are there's a lot of issues still in computation. But these fast algorithms make the methods more practical. OK, so this work we did with GE and with John Baptiste and Zheng Xie actually went into the GE's product, and it's called VEO. It's MBIR implementation. The product's called VEO, and you can buy it if you buy a CT scanner in the US. And I think, so some of the results I'm going to show you here are from that. But OK, so these are some old results, but I think they illustrate the method pretty well, which is over here we have an iterative reconstruction of a phantom. This is, these both are conventional filter back projection reconstructions. They're actually probably a cone beam reconstruction algorithm, but they're approximately, they're a direct reconstruction similar to filter back projection. And over here, this is optimized for bone, so it has high resolution and high noise. And this is optimized for soft tissue, so it has low resolution and low noise. Now, over here in this chart, it shows the number of line pairs per centimeter of resolution in each of these methods. And if you look at the chart, you see that this reconstruction that's iterative has the resolution of the bone, but it's got half the noise standard deviation of this soft tissue reconstruction. So half the standard deviation is 1/4 the power, and that translates approximately to, and in practice this is sort of typical, 1/4 the dosage. So if you're a patient being scanned, you only have to be exposed to about 1/4 the X-ray exposure in order to get the same noise and you still obtain the higher resolution. So you kind of get your cake and eat it too in these methods. And you can get some pretty dramatic results. This is a reconstruction reformatted in a coronal direction. And this is the same data set. This is a conventional cone beam reconstruction. And this is iterative reconstruction. And you can see here that's a kidney stone. So I think this kidney stone is a nice example because you can see that, in fact, it's very hard to see here. There's real information that's being extracted out of the data that you would otherwise lose. And one of the reasons is that the projections, some of these projections are much more reliable than others. If they pass through bone, they're heavily attenuated. So actually working from the direct reconstruction, it's a sinogram data, actually extracts more information. And these are just some more examples that just to show you. Here's a pediatric example. This is compared to ACER, which is essentially like a processing algorithm that occurs after reconstruction. And you can see that you can still extract more information through the iterative reconstruction. But the price you pay for this is the computation is high. OK. So now that kind of gives you the basic framework. So we recently started working with material scientists on a variety of different problems in imaging and using some of the same kinds of techniques. And this work was done with Peter Voorhees, a student of mine, Aditya Mohan, and Mark de Graaf, and Zhao from the Advanced Photon Source at Argonne National Labs. So synchrotron imaging is really kind of picking up steam as a cool technique that I think you're going to see used a lot more in the future. And what's happened is, and this is sort of I'm not a particle physicist, but it's the impression I get, that a lot of these facilities were built, these synchrotrons were built for doing particle physics. But now with the LHC, the Large Hadron Collider, and other very high energy experiments, they don't really need these so much. So they've been repurposed for generating X-rays as X-ray sources. So you have the electrons travel around in this circle, and then at each of these points, they're accelerated tangentially to sort of go around the ring. And at that point of acceleration, they generate X-rays, because accelerating electrons create X-rays. And you get beam lines at each of these points. And at each of those points, you get very highly collimated, intense X-ray beams that are very monochromatic. So you can do a lot of very interesting physics and biology with these systems. And so working with Peter Voorhees, we collected data. And I just say that there's a number of these facilities across the country. One over here is at SLAC, Stanford Synchrotron, and also Cornell. And we also work with the Advanced Light Source, which is at Lawrence Berkeley Laboratories, more on the computing side. But anyway, so the interesting thing is you have a sample here, and you have a source of X-rays coming in. It's like a parallel beam. And in this experiment, there's a fundamental scientific problem that Peter Voorhees wants to solve, which is understanding the solidification of solids. So this is very important in applications like jet engine design. It turns out that a turbine blade in a jet engine is a single crystal of metal. And in order to form that single crystal, you have to understand the processes of solidification that occur. And you get a thing called dendrites, which is just like what forms on your windshield in the morning if you live in Indiana, okay? These crystals that grow out like trees. You'll see them in a minute. So you want to see that formation. So this is really a time-space reconstruction problem. So, and you can see over here, this is just an example. This is a slice. And what happens is that the light regions are the aluminum, and the dark regions are the liquid aluminum with some amount of copper in it. So the copper is more absorbent of the X-rays, so you get contrast. So it's like doping of the aluminum for the purposes of being able to track it. Okay, so now what happens is you have an imaging sensor which is about 2,000 by 2,000 pixels. To do reconstruction, you need 2,000 views. So if your frame rate of the pixel of the camera is like 100 frames per second, it would take 10 seconds to take enough. 20 seconds to take enough frames in order to do one reconstruction. So traditional reconstruction, you take 2,000 views, do a reconstruction. 2,000 views, do reconstruction. So this is very slow acquisition. So the question is, how can you do this in a way that gives you better time resolution so you can observe the crystal growth processes? And so what we did is, working with material science people and the synchrotron people, we said, well, look, the traditional view, we don't need to stick to that. We can actually have the object rotate around faster and then interlace the views. So basically what happens is this would show that if you have n views, this would be the traditional case, they're all in order. But you can take every other one and then take first the even ones and then the odd ones, say, sort of like interlaced TV. Or you can do more interlace frames. And now the disadvantage of doing too much interlacing here is that the object has to rotate too fast, and that can disturb the experiment. So we pick some kind of intermediate point, and then we do a time-space reconstruction of the 4D object in time and space. So this just shows the variable k here represents the number of what we call subframes. So if k equals 1, you have the traditional case. K equals 2, you have 2 interlaced passes. K equals 16, you almost get sort of a randomized sequence of points in view angle. And now, in addition to this, we can also do reconstructions at any time resolution we want. That's one thing that's sort of counterintuitive about these model-based reconstruction algorithms. It doesn't require, like in filtered back rejection, you do discrete reconstructions from sets of views. You can reconstruct at any time you want. So typically what we find is we want to do about as many reconstructions in time as equal to k. So if we have 16 interlace frames, then we want to do 16 reconstructions. Okay, now this shows the result. So this is on simulated data to illustrate the benefits of the approach. In the real physical problem, we just did the best case on the synchrotron because the synchrotron time's expensive, okay? But over here we have a phantom, okay? And this is what we call the time interlaced MBIR. So we call it TIMBIR. That's our kind of fancy acronym. Okay, so now this is MBIR with no interlacing. And this is traditional filtered back projection with no interlacing. And this is filtered back projection with interlacing. So what we see, first of all, is that the reconstruction using this time interlaced MBIR is quite good. But the surprising, and then of course if we don't do the interlacing, we do MBIR, well, we get some improvement, but not the kind of dramatic increased time resolution. But the interesting thing here is that if you do traditional filtered back projection with the interlaced data, so if you collect the data in the innovative way, but you don't do an innovative reconstruction, you get a very bad result. And that's sort of illustrating this concept that it's the synergy between the forward model and the prior model that really produces the better quality result. So you really need both, okay? And this is just showing the same thing along a different axis. This is y and time, okay? But so the key issue is this, that if this is if you're using filtered back projection and the fancier MBIR reconstruction along this axis, and you're using conventional sampling and interlace sampling, it's really the synergistic interaction between those two things that produces the improved result. So here, this just shows the results of actually the real data. So here you can see, it's kind of interesting. Let's see if oh yeah, there it's playing. So this is the light areas are the solid material that's formed through solidification because the copper leaches out of the aluminum. And this is just showing a 2D slice. In fact, we did 2,000 by 2,000 by 1,000 by time, 16 in time, 4D reconstruction, okay? So here you can visualize the segmentation. So this is done with a k equals 16. So this shows, I think this will repeat. This shows the growth of the dendrites. Is it going to repeat? Yeah. This shows the growth of the dendrites. And the important thing to know here is that this is the time resolution of this reconstruction is 16 times greater than the classical method. So by doing this, we're able to see things in the growth of these dendrites that would otherwise just not be possible to see. In fact, that entire time sequence of reconstructions would be a single time frame that was just all blurred, okay? So this is allowing us to basically discover new science, or allowing Peter Voorhees anyway. Okay, so now, the next example I want to give you is electron microscopy. It's, we've worked a lot with Larry Drummey, Mark DeGraff, and Jeff Simmons at AFRL. And my student here is Venkat, who's I think maybe out in the audience, who really did all the work here. He's a really great guy. Okay, so what happens is it's a similar kind of story with, there's actually there's many, many different modes of electron microscopy. But the one that we're considering here is what's called transmission electron microscopy, where you have a source of X-rays. I think they're, of electrons. I think here they're the bottom. I should know this, but on one side is the detector and one side is the source. So let's say that the source of electrons is up here, and it goes down, and the detector's down there, okay? And the sample's in the middle. So, and then in addition, you can tilt the sample. So you get a sequence of, you can see there, you get a sequence, but it's limited angle. You can't get 180-degree rotation of the sample. And from that, you want to do 3D reconstructions of the objects, so you can do basically imaging of nanoparticles and nanostructures. Okay, now there's two very fundamental, this is sort of tutorial, but I think it's really, it took me a while to understand this when I got into this, that there's two sort of fundamental views of imaging. One is bright field and the other is dark field. In bright field, the idea is that the detector is at the point where the the direct beam would hit. So if you take the sample out, you'll get a bright signal. In dark field, you detect the scattered electrons. So if you take the sample out, the beam will go directly through it and you will detect nothing. So in dark field, the background is dark, and in a bright field, the background is bright. So both kinds of mechanism can be used. This is preferable in materials imaging for 3D reconstruction because you don't get a thing called Bragg scatter, which I'll talk about in a minute. Over here, you get Bragg scatter, and that's sort of a confounding problem. In biological applications, this is more widely used, bright field. Okay, so I'm going to talk about bright field. We've also done dark field. Okay, now in bright field, this is an example of, I think, aluminum nanoparticles. Okay, so it's kind of interesting. Oops. Okay, I want to play that again. Now, when you look at this picture, notice the little particles flashing. Oops. See how they flash? The flashing condition is caused by the fact that metals are crystals. So as the electrons pass through the metal particles, when they're aligned with the crystal structure of the aluminum, they scatter coherently, and that causes the beam to deflect away, and you get a dark image at that position, right? So the problem is that the conventional wisdom is that you can't do reconstruction with a bright field data for materials like this because of the effects of Bragg that violate what's called Beer's law, or the exponential decay. So, okay, so we kind of, in a model-based framework, though, you can do reconstruction with this kind of information. You just need to model it correctly. So we took a very simple, very crude model, but it really illustrates the idea, which is that rather than just, so this equation looks like a mess, but G here is the data, A is the forward operator of the projection, F is the unknown reconstruction. And normally you would square this error, but instead we pick a function, okay, which is a square, but beyond some threshold, it says, look, something's going wrong with this data, so we're just not going to trust it anymore. And we call this a generalized Huber function because the Huber function is continuous at this point. It's a continuous derivative, but this is a discontinuous derivative. Now, there is some, you can also flatten this out, and that's sometimes called like a weak spring model. But we don't do that because then it would not be a proper distribution. By having this tilt, it's a proper distribution, and we can estimate the parameters, the hyperparameters of this model as part of the reconstruction process. So basically, this accounts for the fact that the Bragg scatter is not modeled correctly. So using that, we used this data and did reconstructions. So this shows the reconstructions. Over here is the filter back projection reconstruction from the bright field Bragg data. And you can see that you get a lot of streaks. The quality is very poor. And this is why people just conventionally think that you don't want to use bright field data for reconstruction. So over here, we did, this is with MBIR, just straight up MBIR actually doesn't work too badly because it weights the projections that are highly attenuated much less, so they don't cause as much damage. But with the anomaly correction, we can get better quality results with less. And this just shows that was a XZ cross section. This is XY. So this is sort of looking at a cross section as you move into depth into the sample. And you can see that we kind of get more uniform reconstruction, but much better than sort of conventional techniques. Okay, now you got like, here's kind of just to illustrate the fact that you get auxiliary information in these modeling techniques, which are kind of interesting. So as part of the optimization process, we use a thing called majorization techniques that I haven't had time to talk about, but they require basically that you essentially label each point as within anomalous or non-anomalous. So you get a segmentation for free as part of the reconstruction process. And the segmentation is shown on the bottom for each view. So a particle is white when it's in the Bragg condition in the projection. So we can sort of use this information as auxiliary information that's valuable potentially to the material scientists that are understanding the material. So, so basically what you could do is take this segmentation in 3D. You can then take the reconstruction, segment it into individual particles, correlate the forward projection of the particles with the areas where you have anomalies, and from that you get a Bragg feature vector for each particle that describes sort of the conditions under which it's in, the tilt at which it's in Bragg. And this just shows how we've done that. So this kind of information can be useful in understanding these materials. OK, so now here's a, let me see, I'm kind of running. OK, so here is one thing I'm not going to have a whole lot of time to talk about, but I just want to touch on, is the idea of advanced prior models. So the prior model I talked about was really very, very simple. In fact, sometimes we call it a bizarrely simple prior, OK? A BSP. So, the question is, can you come up with better prior models of images? Certainly, like yesterday in the plenary, we talked about very high-level prior models, so you can have different levels. But even something which could be trained to understand the aspects of real physical data, I won't be able to go into this a lot, but there's a lot of work being done. I'm sure people are familiar with dictionary patch-based methods, KSVD, non-local means, BM3D, bilateral filters, and recent work in Gaussian mixture models. Some of these things are truly explicit models, but a lot of them are just actually denoising algorithms. And denoising is like a great framework in order to study problems of modeling, because it's sort of the purest forward model of just the identity operator. Okay? But we came up with a methodology. This is work by Venkat, on where you can take sort of any denoising model, and I put any in quotes here because there's some mathematics in there, but loosely speaking, you can take any denoising model and plug it in as a prior in an iterative loop in which we use this ADMM algorithm to do the updates, and it's sort of a principled approach. But it allows you to sort of study some of these different models and to see that, yeah, there's a lot of potential here, but different models work better and worse in different kinds of ways. So this is just a simple deblurring problem. And here we see that we compared KSVD, BM3D, which is a denoising algorithm, which this PLOW is something by Peyman Millenfarb, which is similar to like a non-local means kind of thing. This is total variation, and this is the prior model I described. And you can see that in this application, the KSVD worked very well. Here's another case where you could do this in painting. So for people in this field, they know that a very small subsampling, a very sparse subsampling of the points in the image can be used to reconstruct actually the image, and amazingly well. So here you see that actually the BM3D worked quite well in this case, whereas the KSVD didn't work as well. So trying to figure out how to select the best prior model for applications is important. And just to see that there's a lot of low-hanging fruit in this area, particularly in scientific applications. This is work we're doing with Garth Simpson at Purdue, who's a chemist who has got a lot of expertise in optical microscopy. And he has a system for scanning an optical, basically an optical beam across a sample so that he can image in time and space by scanning this beam. And if I sort of play this, I think you'll get the idea. So this is the actual data you collect from the microscope. But from this data, then, you can form. This is just, I'm sure we can do a lot better than this, but this just illustrates it. You can form the reconstructed image in time and space. So this dramatically improves the time-space resolution trade-off you have for this optical imaging system. Okay. Now, the last thing I want to talk about is something that's kind of sort of newish work that we're doing with Greg Buzzard at Purdue, and Dilshan is a student of mine at Purdue, and it's in dynamic sampling. So, oops, what's this thing doing? Oh, okay, that's my. I think it requires that you crash at least once per presentation, so we're good. We're done with that crash. Okay, it should be fine now. It got it out of its system. Okay. There we go. Okay. I just want to point out that signal processors like to take pixels one at a time. I like to pick on signal processors. I'm sorry. I'm one, so I'm allowed to do that. they like to take pixels one at a time in order from left to right. It's very orderly and it makes them feel good. But the thing about it is, if you really think about it, it is the optimally bad way of collecting data, okay? I mean, if you went out and tried to pick the worst possible thing you could do, this would be it, because every new sample you're getting gives you the minimum possible new information about your data, right? So this is really not a good way of collecting data, okay? Now, another way you might do, which I think random sampling has become, random projections and sampling are sort of popular these days. So I'm sort of maybe trying to make a subtle point here, which is that another thing you might do would be to take random samples in the image, because these might be maybe more of a blue noise pattern. So random sampling is a lot better than the previous thing I showed you, but it's still not necessarily optimal. I mean, humans certainly do different things when they look at a scene than take random points. But at least every new point you got is minimally, it has very little correlation with the previous ones, right? Because it's taken at a very different point, okay? Now, so then the question is, well, what's the optimal thing to do? When I say optimal, I really mean greedy optimal. So at least for each new point, what's the most informative thing? There's another question you could ask, which is if you're going to, or after the sequence of points, which would be best? That's much more complicated. But at least for each new point, which one would be most informative, okay? Well, there is a theory of optimal experimental design which gives you some insight into this, and there's been a fair amount of work done recently on some of these problems. So the idea is this. You can mathematically say, well, each new measurement is sort of a linear projection of the full data set with some noise, okay? And this measurement here is the full vector of all the measurements up until that time. And then you could compute what is the conditional mean and conditional posterior mean and posterior conditional variance. So this is the variance of the conditional variance of the image given all the data you know up to that point. And then you could pick the direction which maximizes the variance in the conditional variance, okay? So in other words, you're picking the pixel where the uncertainty, given everything you know up to that point, is greatest, okay? Then you can take that direction, augment the matrix of measurements, and go back and repeat, okay? So, okay, so that's what this says. It's measure the signal, find the posterior covariance of the image, select the pixel with greatest variance, and add a new row to matrix A. Okay, now interestingly, well, I find it interesting, that if everything in your problem is Gaussian, it says that this step can be pre-computed before you collect any data, because the conditional variance is not a function of the data. If you have jointly Gaussian random vectors, then the conditional variance of one given the other is not a function of the data. So all this can be computed in advance, but intuitively, you know the humans don't do that, right? So that really just says the data is really not Gaussian. So if this is the prior manifold, the intuition is this. If you know that the solution is over here somewhere, if your data up to this point has told you that on this prior manifold, the solution is somewhere in this region, then what you really want to do is you want to measure along this direction so you can reduce your uncertainty in sort of the perpendicular direction, you'd say, right? So your uncertainty of the measurement manifold, you want to be perpendicular to the prior manifold. But if you know that the solution is actually over here, then you want to measure in a very different direction. You want to measure this way so that you get your uncertainty manifold is along here, right? So intuitively, when things are not Gaussian, your measurements should be very dynamic. That your previous measurements should tell you a lot about what you want to make your next measurement. The problem is that this is nice in concept, but the computations of computing the posterior covariance could be very complicated. So generally, these things are not possible to calculate in closed form. But you can do it using just brute force computer power, right? You can use the Hastings-Metropolis algorithm and do sampling of the posterior distribution using Monte Carlo methods, right? So in that case, what you do is you have a measurement, you generate samples from the posterior using Monte Carlo methods, and then you compute the empirical mean and variance at each pixel from those stochastic samples. Then you pick the pixel that had the maximum posterior variance, and you repeat, okay? Now, if you do that, this is just a 1D case. this is what happens. So this is the signal here, and this will those little dots are the places where you've taken a sample. And what will happen is you'll sort of discover one of these little blips, and when you discover the blip, you'll take more samples near that blip to try to define the blip's location more accurately. Now, this doesn't come out of looking at the signal and seeing where the edges are, because it doesn't know anything about that. It comes out of a prior model, which is like a prior model I described, that knows that edges have this statistical behavior, and it just looks for the pixels with the highest conditional variance. So now the problem is, if you go to 2D, you'd say, well, this is computationally intractable, but it's actually not so bad. And the reason is this. Well, first of all, there's two steps. First, you're going to generate a sequence of stochastic samples from the posterior distribution. So these are like particles in a particle filter. So say we have 20 of these images. That means we keep 20 images, each of which is a random sample from the posterior. And then we look at each pixel, and at each pixel we calculate the variance of that pixel, and we find the pixel that has the greatest variance across these stochastic samples. Then once we pick that pixel, and we make the measurement of that pixel, based upon that measurement, we do a Hastings Metropolis update of just a window about the pixel, because we assume there's some kind of locality in the model. So this turns out to be computationally pretty efficient to do. So what you get then is you get something like this. So the red points are the points where a sample was taken. And what will happen is that you sort of take points until you discover something, and then you take more points. So this comes out, this behavior isn't built into the algorithm. It comes out of it from the point of view of just trying to measure the most informative points. And over here is the reconstructions you get. So these are the map reconstructions given the subset of points you've measured. And you can see where it'll find something, and once it finds something, it sort of explores it. Right? Some people call this, Yelena Kovacevic does something similar to this, and she and both my collaborator call this like the battleship game, if you remember that from kids. Okay? So, okay, and this just shows that this is, okay, so the real application of this is we're working with Tony Fass at Georgia Tech, is on dynamic sampling with scanning electron microscopy. So in scanning electron microscopy, there's a zillion modes, but they require that you go and make a measurement. Often the measurements you make at each point are very complex and expensive to execute. So you'd like to be able to take the minimum number of measurements and scan around for the important features. So this is a simulation of, this is an electron, this is an SEM scan. And we ran this sort of algorithm, and it just gives you a sense of how it works. So you get points. It does a similar kind of thing. Of course, this is less of a toy example, so there's more fine texture that it's sort of discovering. And remember, this is with what I call one of these bizarrely simplistic priors. If you had a prior that was designed to really model this image more accurately, then you could presumably have more intelligent selection of the points. But I think it does a pretty reasonable job. OK. So then Thrasius, I gave this talk at Northwestern University last weekend. Thrasius made a really fantastic point, which I have to say here, but I'm really not the expert. So if you think what I'm saying is wrong, complain to Thrasius. So this is really, and amazingly, I had not thought about this at all until he pointed it out, which is very much like the saccadic movement of the eye in human vision. That it really sort of finds features and explores them. And there's been a lot of work done in this area. And some of the seminal work has been done by Stark, Predavera, and Nava. I don't know how to pronounce that. I'm sorry. OK, anyway, there's two mechanisms. One is called bottom-up, and the other one is called top-down. OK, so in bottom-up, you see individual features like pop-out that you attract your attention. In top-down, you have some sort of cognitive process of discovery. Interesting, the top-down really corresponds to the prior model in what we've shown here, and the bottom-up corresponds to the sensor model. So it's kind of an interesting observation that the same mechanism has grown out of something that doesn't know anything about image edges, really. It's just going around greedily looking for the most informative next pixel. OK, so, OK, just to wrap up, OK, major directions for integrated imaging. OK, so First of all, the key issue is the creative design of sensor systems. So not just throwing the data over the wall to the signal processing people so that they can make the best image, but jointly designing the system and the algorithm. It increases the design envelope so you can do a lot of things that you might otherwise not think would be possible, okay? And this sort of creates, I think, an explosion of possibilities. We're looking at all kinds of different modalities and intermixing them in complicated ways, okay? Also in dynamic acquisition. So the forward model accounts for complex nonlinear parameters and models. So you don't have to have a linear forward model. You don't have to know all the parameters of your system. You can estimate them during the reconstruction process. And there's this synergistic interaction between the forward model and the prior model. Just doing one or the other by itself doesn't solve the problem. People will often say to me, is it mostly the forward model or is it mostly the prior model? Can you show me how much benefit I'm getting from either of those? And I say, well, I'd like to be able to answer that question, but the answer is it's multiplicative. It's synergistic between the two. And then the other really important thing is that these are all about communities, which sort of makes it fun. That it's not something you do by yourself, you know, in your office with the door shut very tightly. It's something you do with groups of people interacting, interdisciplinary groups, where you have experts in the application, experts in the modality, physics, and they understand what can be changed. Often they'll say to you, well, it's too bad you can't do this. And you say, oh, yeah, you can do that. It's easy, okay? So working together in teams is critical. And that's it. Thanks.